Good morning. I'm Dr. Niti Maheshwari, Assistant Professor, Applied Science and Humanities Department, Ajay Kumar Garg Engineering College, Ghaziabad. In my last lecture, I was discussing about phase rule. The different topics that I covered under phase rule were what are the meaning of phase, components and degree of freedom, and how this equation was derived. And I also continued my lecture for one component system, and under one component system I was describing the water system. So once again, giving a brief background about water system. Water, it exists in three different phases: solid phase, which is ice; liquid phase, which is water liquid; and it also exists in water vapor phase. So these are different phases of water, and these phases, they at certain temperature and pressure remain in equilibrium with one another. So if we see the phase diagram of water system, then if I make the temperature pressure diagram for water system, this is the variation of temperature in degree centigrade and variation of pressure in atmospheres. Then the water system typically shows this is the diagram for water system. Here ice is the stable phase, then water liquid and water vapor. So this is the three different phases of water. So here we can see at low temperature and pressure, the two phases which are going to be seen is either water vapor or water solid, that is ice. And this area, complete area, consists of water vapor, this is of ice solid, this area comprises of water liquid. And the point or the three phases, these three phases, they meet at a particular point, and this point is known as triple point. And at this triple point we can see that the vapor phase, the ice phase and liquid phase, all the three phases are going to meet at this particular point. Now this curve is the this curve is the sublimation curve of ice. Here ice and water vapor, they are in equilibrium on this curve. Similarly, this is the vaporization curve, and on this line water liquid and water vapor, they are in equilibrium. And similarly, this is the melting point curve of ice, and on this curve ice solid and water liquid, they are in equilibrium. Generally for other substances, all the curves, they ought to have a positive value. That means as we increase the temperature, pressure also increases. But in the case of water system, the melting point curve of ice has a negative slope. In this case you can see, on increasing the pressure, the temperature is going to decrease, and that means ice melts with a decrease in volume, and it can be contributed to the structure of ice because ice has cavities inside them, air cavities. So ice is solid, but it has air cavities in it, and when we heat ice, the hydrogen bonding which is present between the molecules, it breaks down. As a result, the water molecules, they compress, and there is reduction in the volume, because in ice, because of the hydrogen bonding, the water molecules are further apart, but on heating these hydrogen bonds, they break and the water molecules, they come closer. So, it is also responsible for the phenomenon that the water contracts from 0 to 4 degrees centigrade. Because of this contraction, this has a negative slope, and this triple point, you can see the three phases only at a particular temperature and pressure, and the temperature is near about 0 degree, that is 0.0098 degrees centigrade, and the pressure corresponding to the triple point is 0.006 atmospheric pressure. And at 1 atmospheric pressure, this line cut the melting point. This is the at 1 atmosphere, this is the freezing point, and at 1 atmosphere this line cuts the vaporization curve. This is the boiling point of water, that is 100 degrees centigrade, and the freezing point, that is 0 degree centigrade. And at critical point, this curve extends up to the critical point, which is 314 degree centigrade and 218 atmospheric pressure. After that, the two phases, they submerge into each other, interconverge into each other, and result in the formation of only one phase, that is a denser fluid, which is the also known as supercritical fluid. Now, I also want to discuss about, here in the diagram, you can see a dotted line. Here we can see a dotted line which starts OC dash. Now, this line OC dash which is seen, it is the extension of AO curve. The vaporization curve extends and then it is seen as OC dash curve. This is the metastable curve of water. Metastable curve, here below the freezing point, water does not get converted into ice, it stays into water liquid state. And below the freezing point, if water is existing in the liquid state, it is not the stable state. So, this AO, which is the equilibrium between water liquid and water vapor, it continues in the dotted line OC dash. And this water liquid below 0 degree, as I said, it is not a stable phase. It can be converted into a stable state by adding a small amount of stable phase, and the stable phase at this temperature is ice. So, if I add small amount of ice to the metastable water liquid, then the water liquid is going to quickly get converted back into the stable state, that is the ice. So, the different states, ice, water and water vapor, in the areas the degree of freedom is 2 according to the equation F plus P is equal to C plus 2. This is one component system. If phase is 1, according to the equation F plus P is equal to C plus 2. Since water system, C is fixed as 1, if P is equal to 1, then F is equal to 3 minus 1, which is 2. So, degree of freedom will be 2. If we are talking about these curves, then in these curves, two phases are in equilibrium. So, the number of phases increases, our degree of freedom decreases. That means the degree of freedom on the curves is only 1. You can either vary the temperature or the pressure. As our vapor pressure becomes dependent upon temperature, so if temperature is fixed, vapor pressure will also be fixed. Similarly, if we talk about this point, at this point, as I said, all the three phases, they are going to coexist at this point. That means degree of freedom, if I calculate at the triple point, then the number of phases is 3 at the triple point, because at triple point the equilibrium that I am talking about is between ice solid, water liquid and water vapor. And to see all these three phases together, my temperature and pressure, they ought to be fixed, because this equilibrium exists only at one value of temperature and one value of pressure. So, I do not have the freedom to vary either the temperature or the pressure. So, here the degree of freedom comes out to be 0. So, at triple point there is 0 degree of freedom, or my system is non-variant at triple point. And if suppose my number of phases become 4, then the degree of freedom will become -1, which means that for one component system, the maximum number of phases which can be in equilibrium are 3. I cannot observe all the 4 phases together for one component system. Either one or the other phase will disappear, only then the another phase will take its place. That means for one component system, at a maximum only 3 phases can be in equilibrium. For example, in case of sulfur, sulfur exists in 4 phases: sulfur rhombic, monoclinic, liquid and vapor. But I cannot see an equilibrium between all the 4 phases together. So, the maximum number of phases which can be in equilibrium for one component system is 3. So, here as I was discussing, this OA, it is the vaporization curve, and water at any given temperature is associated with vapor. With increase in temperature, there is an increase in vapor pressure, and the rate of increase is higher at higher temperature. So, the vaporization curve, it starts at the freezing point and extends up to the critical temperature. So, here I have done the calculation for the vaporization curve, how my degree of freedom comes out to be 1 and the system is univariant. Then the sublimation curve. The sublimation curve, it represents an equilibrium between ice solid and water vapor, and with the decrease in temperature initially, the vapor pressure drops steeply, followed by slow decrease. Now, this sublimation curve, it can be extended below the B part, and along sublimation curve, the 2 phases ice and water vapor, they are going to be in equilibrium with each other, and again on this curve the degree of freedom is going to be 1. That means the system is mono or univariant. Then again for the fusion curve, the fusion curve, it represents ice solid and water liquid in equilibrium state, and the curve slopes towards pressure axis, indicating melting point of ice is decreased by increasing the pressure. As I have already discussed, as ice occupies more volume than water, whenever pressure is increased, ice melts to form water, which is accompanied by a decrease in fusion temperature. Again, the system is going to be univariant along the fusion curve or the melting point curve. Now, the line that I was discussing about the metastable curve, which is also the supercooling curve, and it says that water does not always freeze at 0 degrees centigrade. If the vessel containing water and vapor is perfectly clean, there is no impurity and it is also free from dust, then it is possible to supercool water below its freezing point. And the curve OA, it represents the vapor pressure curve of supercooled water. And this curve represents a metastable system which reverts back to the stable system on slight disturbance. If I add small amount of ice, cause a disturbance in the system, then the supercooled water will get converted back into ice. Triple point, as I have already discussed, the three phases, they are going to be in equilibrium with each other at a particular temperature and pressure, and the system is going to be non-variant, therefore the degree of freedom will be 0. And the areas where only ice is present or only water liquid or only water vapor is present, at that areas the degree of freedom is going to be 2. That means the system is going to be bivariant. That is, I can individually vary temperature as well as pressure. Even then my phase is not going to change. Now, I will be starting with module 4 with water and its treatment. The topics that I am going to cover is hardness of water. What is hardness of water? What is disadvantages of hard water? What are the different techniques which are being used for water softening, like Calgon, like zeolite, like lime soda, ion exchangers, reverse osmosis, and what is the water treatment method for boiler feed by internal process. The reference that I have taken, the engineering chemistry book by Jain and Jain, then engineering chemistry by Shashi Chawla, and engineering chemistry by Ville India. Now coming first to the hardness of water, or rather starting directly from hardness of water. Now the water is the basic necessity, and the quality of water is degrading day by day by the addition of different materials from different sources. And because of these inlets into the water bodies, whether the domestic water is running or the factory outlet water is running in the streams, water streams or rivers, ultimately they are landing into sea. The water quality is degrading day by day. Therefore, there is a requirement for the water treatment. And since the metal is increasing in water, metal content in water is increasing, therefore the metal which is present in the water, they cause hardening of water. So hardening or hardness of water is nothing but it is that characteristic which prevents the lathering of soap. If we wash clothes and rub soap, then that soap should produce lather. But instead of lather, if a precipitate, a scum is being formed, which shows that the water that we are using is hard water and it contains certain salts which are not letting the soap to form lather. Therefore, for the cleaning purposes, we require excessive amount of soap. So, coming back to the hardness, hardness in water is that characteristic which prevents the lathering of soap. This is due to the presence of certain salts of calcium, magnesium and other heavy metals which are present in it. A sample of hard water, when treated with soap, it does not produce lather, but it produces a white curdy precipitate which is known as scum. And the precipitate which is being formed due to the formation of the insoluble soaps of calcium and magnesium. So here soap, sodium stearate, long chain fatty acids, sodium salts they are, and when they react with the water, and if in water if calcium, magnesium or heavy metals they are present, then these metals they react with soap to form calcium stearate, magnesium stearate, and these calcium and magnesium stearates they occur in the form of precipitate. Therefore, the lathering of soap is prevented. And why does soap consume lots of water? You can see that soap For example, I have taken as sodium, they are sodium salts. So, here I have taken sodium stearate, and if we add soft water which contains very less concentration of these calcium, magnesium and heavy metals, they form NaOH and stearic acid. And this stearic acid, it reacts with sodium stearate, and which results in the formation of leather. But in the case of hard water, this sodium stearate, it reacts with calcium ions. Suppose hardness is because of the calcium salt. So, this sodium stearate, it reacts with calcium ions, resulting in the formation of a precipitate of calcium stearate, and this precipitate hinders in the leather formation of the soaps. So, hard water contains bicarbonates of calcium and magnesium, then chlorides, sulfates of calcium and magnesium. These combine with the soap molecules to form precipitates of calcium and magnesium salts of soap. As a result, I have already discussed, this is what the curdy white precipitate is of. So, as a result, the soap is wasted and the hard water does not produce leather with soap. Now, the soft water, when treated with soap, it produces leather and consumes less soap, and it is due to the absence of dissolved salts of calcium and magnesium. If I discuss about the dissolved salts, then there is temporary hardness, which is due to the presence of calcium bicarbonate and magnesium bicarbonate. And here the sodium stearate reacts with water to form stearic acid and NaOH, and hence they produce leather. Coming to the types of hardness. Hardness is of two types, temporary and permanent. As the name suggests, temporary hardness is that hardness which is caused by only bicarbonates of calcium and magnesium, and this hardness can be removed by simple boiling process. Even at homes, if we boil water, then a precipitate along the side of the utensil, a white precipitate is formed along the sides of the utensil. That precipitate, if we filter this water, we can remove the precipitate from water, and this white precipitate, small drops of precipitates which are being formed at the surface of water or at the utensil surface, this is because of the bicarbonates of calcium and magnesium. And when we boil water, the calcium bicarbonate, it gets converted into insoluble calcium carbonate, and similarly magnesium bicarbonates, it gets converted into magnesium carbonate, and both are insoluble in water. So, we can filter it off. Therefore, the type of hardness which can be removed by simple boiling process is known as temporary hardness, as it is only because of the bicarbonates of calcium and magnesium. Therefore, this hardness is also known as carbonate hardness, and since bicarbonates of calcium and magnesium, they are also responsible for making water alkaline, they are also responsible for the alkalinity of water. Therefore, this hardness is also known as alkaline hardness. Second type of hardness is the permanent hardness. By saying permanent hardness, I mean that hardness which cannot be removed by simple boiling process, and this hardness is caused by the chlorides and sulfates of calcium, magnesium and other heavy metal ions. Other heavy metal ions like aluminium, like iron, like manganese, and since they are caused by the chlorides and sulfate, therefore this hardness is also known as non-carbonate hardness, and as they are not responsible for alkalinity in water, so they are also known as non-alkaline hardness. Some examples or some salts which can cause permanent hardness are the calcium chloride, magnesium chloride, calcium sulfate, magnesium sulfate. Now coming to degree of hardness. Now the degree of hardness is usually expressed as parts per million ppm, and it may be defined as the number of parts by weight of calcium carbonate present in 10 to the power 6 parts by weight of water. How many parts by weight of calcium carbonate is present in 10 to the power 6 parts by weight of water? So this is the degree of hardness. And if we want to change the hardness into equivalence of calcium carbonate, then this is equal to the mass of hardness producing substance into chemical equivalence of calcium carbonate divided by chemical equivalence of hardness producing substance. This interconversion I am going to take later. Now, calculation of equivalence of calcium carbonate. I cannot individually take the hardness of calcium sulphate. If I am taking a water sample and it contains calcium sulphate, magnesium sulphate, calcium chloride, then the hardness produced by calcium sulphate will not be equal to hardness produced by magnesium sulphate. So, in order to make a common factor, a common ground of all, then we have to convert the hardness in terms of equivalence of calcium carbonate. And how we do that? We convert the hardness into calcium carbonate equivalence by using the equation. The equivalence of calcium carbonate is equal to the mass of hardness producing substance, how much hardness producing substance is present per liter of water, then it is multiplied by chemical equivalence of calcium carbonates divided by chemical equivalence of hardness producing substance. That means equivalent weight of calcium carbonate divided by equivalent weight of the hardness producing substance, whichever we are using. Here suppose I am taking magnesium sulphate. So, molecular weight of magnesium sulphate is 120, equivalent weight n factor is 2, therefore, equivalent weight will be 120 divided by 2, which is 60. Then we can calculate the equivalence of calcium carbonate, which comes out to be, if it is present 180 milligram per liter, this is the mass of hardness producing substance. Chemical equivalence of calcium carbonate, molecular weight of calcium carbonate is 100. So, equivalent weight will be 100 by 2, which is 50, and this is 60. We get 150 milligrams or pp, 150 milligram per liter or parts per million. Now, coming to units of hardness. Units of hardness, different units are there. The first unit is degree Clark. Degree Clark says that if in a 7 into 10 to the power 4 parts by weight of water contains 1 part by weight of calcium carbonate or equivalent salts of calcium and magnesium, then the hardness is said to be 1 degree Clark. Similarly, the second unit is degree French. If in a 1 into 10 to the power 5 parts of water contains 1 part of calcium carbonate, then the hardness is said to be 1 degree French. That is, 1 part of calcium carbonate present in 10 to the power 5 parts of water is degree French, or 1 part of calcium carbonate by weight present in 70,000 parts of water by weight is degree Clark. Next unit is parts per million. Parts per million is, if in a 10 to the power 6 parts by weight of water, it contains 1 part by weight of calcium carbonate, then the hardness is said to be 1 ppm. That means 1 part by weight of calcium carbonate present in 10 to the power 6 parts by weight of water, then it is parts per million. And why the hardness that we are discussing is measured in terms of calcium carbonate? Because this calcium carbonate is least soluble salt in water. Generally, calcium carbonate is not present in water. And second, the molecular weight of calcium carbonate is 100, and this makes the calculations easy. Now, coming back to this interconversion, 1 part of calcium carbonate present in 10 to the power 6 parts by weight of water is 1 ppm. It is similar to 1 milligram per liter, and in terms of degree Clark, it is equal to 0.07 degree Clark, and it is equal to 0.1 degree French, and it is also equal to 0.02 milli equivalence. So, if you want to convert ppm into degree Clark or degree French into ppm, then we can use this interconversion. Now, I have taken one numerical. The water sample, it contains the following salts. It contains calcium bicarbonate, magnesium bicarbonate, calcium chloride, magnesium sulfate, and these are the amounts which are present in per liter of water. Now, we have to calculate the temporary, permanent and total hardness. Now, as I have already discussed, the hardness of soluble salt equivalent to calcium carbonate, we can do the calculations according to the equivalent weight or the molecular weight. So, here it is the weight of the sample which is present in water multiplied by 100, which is the molecular weight of calcium carbonate, divided by the molecular weight of the soluble salt, that is the salt which we are taking here as capital W. Suppose I am taking the hardness due to calcium bicarbonate. Now, calcium bicarbonate was present 8.1 milligram per liter. So, here I am taking 8.1 multiplied by 100, which is the molecular weight of calcium carbonate, divided by molecular weight of calcium bicarbonate, which is 162. So, hardness comes out to be 5 milligram per liter in terms of calcium carbonate equivalence. Similarly, I am converting the hardness due to magnesium bicarbonate into calcium carbonate equivalence, and calcium chloride and magnesium sulfate also in terms of calcium carbonate equivalence. So, here we are converting all these into calcium carbonate equivalence. Now, we know that the temporary hardness is caused by the bicarbonates of calcium and magnesium. So, these two are responsible for causing the temporary hardness, and permanent hardness is caused by the chlorides and sulfates of calcium and magnesium. So, here calcium chloride and magnesium sulfate, they are responsible for causing the permanent hardness. So, if I add these two now, I cannot add simply this 8.1 and 29.2 hardness to calculate the temporary hardness, because we ought to have the hardness caused by calcium bicarbonate is not equivalent to the hardness caused by magnesium bicarbonate. So, for making a common ground, we are converting all the different types of hardness into calcium carbonate equivalence. So, on addition of hardness caused by calcium bicarbonate and magnesium bicarbonate, that means if I add these two, I am going to get the temporary hardness, and if I add these two hardness by calcium chloride and magnesium sulfate, I am going to get the permanent hardness, the hardness which cannot be removed by simple boiling. So, here the temporary hardness comes out to be hardness caused due to calcium bicarbonate adding the hardness caused due to magnesium bicarbonate, which is 25 milligram per liter, and permanent hardness is because of the calcium chloride and magnesium sulfate, which comes out to be 15 milligram per liter, and the total hardness, it comes out on the addition of temporary and permanent hardness, that is adding the two different types of hardness. So, I get the total hardness as 40 milligram per liter. Thank you.